In the previous lecture, we saw how the angular momentum operators end up providing certain measurables. So basically YLM when operated by L square gives you H cross square L into L plus 1 YLM. LZ gives you YLM when operated on YLM gives you MH cross YLM. We saw that the mod of M is restricted by the value of L. In addition, the points that we learnt in the last class was that L plus minus on LZ gives you minus plus H cross L plus minus. So this was seen in the previous class. And also we saw LZ on L plus minus YLM gives you H cross M plus minus 1 L plus minus YLM. So these were the results that we deduced in the previous class, and we will be continuing further to understand few more relations. And what we were able to deduce from this relation was that YL plus minus ends up incrementing or decrementing 1 unit of the M quantum number. You realize that L plus or L minus has no impact on the quantum number L. This is a very important thing for us to understand. Okay, great. So now, having said that, let's try to quickly see few of the things which we commonly ended up determining in all the other models. So let's ask a question: what is the expectation value of LZ? It might be tempting for you to write the entire spherical harmonics in its full glory. It might not be necessary, because let's try to do this. So when you have YLM with LZ, YLM, remember this can also be written as L comma M, LZ, L comma M. This is the Dirac bracket notation. So when you have this, when you operate LZ and YLM, you're going to get MH cross YLM back, and this results in the Kronecker delta. So therefore you're going to get MH cross as the expectation value of LZ. Needless to say, the expectation value of L square will be H cross square L into L plus 1, right? So now let's ask the same thing: what is the L expectation value of Lx? So you might remember L plus minus is given by Lx plus minus ILy. So therefore Lx will be given by 1/2 of L plus L minus. So therefore what will end up happening? The expectation value of Lx is going to be given by L comma M, L plus L minus by 2 L comma M, right? So this can be divided into two different brackets where you have L plus M by 2, L plus by 2 plus L comma M, L minus by 2 L comma M. And what did we learn from the previous deduction is that L plus will change M by plus 1. So you're going to have let's say you get some constant C prime, let's say C prime by 2 L M plus 1 plus L comma M, let's say D prime divided by 2 L M minus 1. So once you realize, you take this constant out, you have two functions that are very different. They basically are different solutions to the spherical harmonics. This will give you an overall value of 0. Similarly, Ly will also be equal to 0. These are very important deductions about the angular momentum operator, because let's go back to the thing that we drew. So this is what we drew for L equal to 1, just as a simple example, ZXY, and you had the Z projection as H cross, and then you had the overall magnitude as 2H cross. This is the other vector. Then you had this one. We were discussing the fact minus H cross square root. We were discussing the fact the theta in this case is 45 degrees or pi by 4, and we were asking what is the value of phi. What one is able to understand from this previous deduction, the average value of the x component of the angular momentum and the y component of the angular momentum are in fact 0. So what this results in is that this vector ends up sampling every possible phi angle. So therefore the average phi angle will end up being 0. That doesn't mean it's always equal to 0. but it just meaning that it's along the x-axis, it just means that for every orientation that it samples in a given xy plane, as a vector in a given xy plane, there is an equal and opposite vector that ends up cancelling whatever the orientation was. So basically you start imagining these as inscribing a cone right about the z-axis, right? So this starts processing about the z-axis is the kind of picture that you are able to imagine. This is very important because this comes back to us in terms of the Heisenberg's uncertainty principle. So what is that we wanted to understand with the Heisenberg's uncertainty principle? When you have Lx and Ly given by I, Lz, and L square comma Lz is equal to 0, this indicates that L square and Lz can be precisely determined by Lx and Ly cannot be. If you might remember, we were talking about the variance associated with sigma A times sigma B is minus h cross square by 4. The whole integral, we had psi star A comma B psi d tau, right? So this is what we had earlier, and we were able to understand once again, yeah, that's why you will not be able to determine the x and y component reliably. Okay, fantastic. So now having said this, let's move on. Let's go back to the question, okay, what happens when you apply L plus minus on y Lm? So this was our question, right? We want to understand what will the constant be, and of course you know you are going to get YL m plus minus 1. So let's say the constant is given as C L comma m, meaning that where you started from, plus minus for saying either it's a plus operator or the minus operator. I would request students to not get confused when I'm doing L plus minus. L plus minus is just because of the fact that these have very similar relationships, and one can derive one and therefore immediately see the other rather than deriving everything from the beginning for the other one. So I don't mean plus minus exist together. This is just for the arithmetic being a little easier. So what are we trying to understand? When you operate L plus minus on, let's say, something like 2, 1, what do you end up getting, right? So you are going to end up, let's say L plus on y2, 1. You are going to end up getting the L quantum number will not change, while the M quantum number will be incremented by 1. So you are trying to say the C plus of 2 comma 1. What is this value? Okay, so now let's ask what happens when you operate L plus on y2, 2. For the value of M, we know that the mod M is restricted between the values of L. So therefore M value for L quantum number equal to 2 cannot exceed 2, so therefore this is going to be equal to 0. This is very similar to what we saw in the simple harmonic oscillator, where when the ladder down operator when operated on the ground state ends up giving you 0. Here ladder up operator when operated on the highest ever state for that given L quantum number also gives you 0. So let's take another example. What is L minus on 2, 1? That's going to give you y2 because L quantum number doesn't change. 1 will end up going to 0 because 1 minus 1 will be equal to 0. So the coefficient you're talking about is C minus 2 comma 1. So similarly L minus of 2 minus 2 will be equal to 0 because you cannot go to a level that's lower than the lowest level that is possible in that given scenario. Okay, fantastic. So basically what we are trying to quantify here, what is L plus minus magnitude, because if you are able to get this, we'll be able to achieve a lot of things. Very good. So how will we get this? We will see in a moment. So before going there, I need to introduce a few more things as we go forward. Alright, so what will be introduced here? We will be introducing what is L plus times L minus. Okay, so how will we get this? In order to get this, we need to understand what is the, how would we write each of them separately. So Lx plus ILy times Lx minus ILy. So we calmly take the product carefully. Lx times Lx is Lx square. Lx times minus ILy is Lx Ly. I want students to be careful and not write it as Ly Lx these are operators which need not always commute. So please be very careful. Next term will be Ly Lx minus I square Ly square. So this can be rewritten as Lx square minus I square will be plus 1. So Lx square plus Ly square plus I Ly Lx minus Lx Ly. So what have I written? I have written this here, and this ends up going here. Okay. And what we are able to see, this is nothing but L square minus Lz square. This we also saw in the last class. And this is nothing but I times commutator of Ly times comma Lx, right? And L square minus Lz square. So now let's say we are operating L plus minus on YLM. This is going to be equal to L square minus Lz square on YLM. And we know that Ly Lx will give you, commutator Ly Lx is minus I h cross Lz, right? Minus I square will be plus 1. So plus I h cross Lz on YLM. So what will this end up happening? L plus times L minus YLM will be equal to h cross square L into L plus 1 minus h cross square M square, right? The I won't be here because the I square would have gotten cancelled, plus M h cross, right? So h cross square, because there will be a M h cross that comes, so there's h cross that already exists. H cross square L into L plus 1 minus M minus 1. Let's say you do this slowly again. L minus L plus on YLM. We did L plus L minus on YLM. That will be equal to h cross square L into L plus 1 minus M into M plus 1. So basically this can be written as L plus minus L minus plus on YLM gives you h cross square L into L plus 1 minus M minus plus 1 YLM. Okay, this is extremely important for us to go forward. Alright, now we have deduced this. Let's keep this result on the side. To 2 pi d phi 0 to pi sin theta d theta c. We are talking about L plus minus on YLM star L plus minus on YLM is equal to the integrand. So when you have this integrand, you know that L plus minus on YLM will give you C plus minus on L comma M, of course with a star, and it will change YLM plus minus 1, right? So similarly this will also get changed. So you're going to get mod C plus minus L comma M the whole square 0 to 2 pi d phi 0 to pi sin theta d theta YLM plus minus 1 star YLM plus minus 1. That will be equal to the integrand. If it's M plus 1, it will be M plus. So we are keeping the same type of operators. Since these are orthonormal functions, you're going to get the integrand I will be equal to C plus minus L comma M the whole square. Okay, the same integrand can also be written in a different way, where it's 0 to 2 pi d phi 0 to pi sin theta d theta. What can be done is to move this operator within this bracket. We can move the L plus minus into the next operator. Remember, there's a complex conjugate that is present, and what is the complex conjugate of L plus minus? That's equal to L minus plus. Basically it gets inverted. So therefore this will end up becoming YLM star, and it will be in the fronts L minus plus L plus minus YLM will be the integrand again. So did you follow what I did? All I did was to take the same integral, move the operator into the other bracket. Since it's a complex conjugate, L plus minus will become L minus plus, and of course since these are operated, it has to go before this operator, not after or after this function. Okay, now having done this, just the moment back we deduced what is L plus minus L plus times L minus of YLM. Let me rewrite it. What did we find? We found L. I'll just write whatever is pertinent in this derivation will be equal to h cross square L into L plus 1 minus M into M plus 1 YLM. So if you realize, this can be plugged into it where you get YLM back, which will integrate. Since these are orthonormal functions, you'll get back 1. Therefore your integrand, which we saw as L C plus minus L comma M, the mod square will be equal to h cross square L into L plus 1 minus M into M plus 1. Let's say you patiently repeated the same process, right, with the plus minus here, there'll be a minus there. So you will get something like this. And therefore C plus minus L comma M will be given by h cross under root L into L plus 1 minus M into M plus minus 1. This is very important. So what did we learn here is that, let's say you end up operating L plus on YLM, you're supposed to get C plus on L comma M, YL M plus 1. So this will be equal to h cross square root L into L plus 1 minus M. No, this will be a minus. Okay, yeah, because I'm not doing plus minus here. Okay, YL M plus 1. So let's take an example. We wanted to ask what is Y10, isn't it? That will be equal to h cross square root value of L is 1, 1 into 1 plus 1 minus value of M is 0, 0 into 0 minus 1 Y1 1, because M value will be incremented by 1 while L value remains same. So this is nothing but square root of 2 times h cross Y11. So L plus on Y10 will be this. And this is nice to have because you know what is Y11, you know what is Y10. We just learned in the last lecture how these can be easily deduced from whatever we have learned earlier about the Legendre polynomials. So this gives you an exquisite handle on how things can be changed. Now let's continue with the result that we have obtained for the ladder up, ladder down operator for the angular momentum, where L plus minus on YLM gives h cross under root L into L plus 1 minus M into M plus minus 1, returning you YLM plus minus 1. So basically the L quantum number remains unchanged while M gets incremented or decremented by 1 quantum unit. Rewriting the same equation here again, I'm just starting to give you an example where when you have the L quantum number equal to 1, M can take the values 0 plus minus 1. Then if you want to write the LZ matrix, this is how it's going to look for a system with L, small l equal to 1. You're going to have a 3 by 3 matrix where you have the brassichet type notation where 1 LZ1 will be the first matrix element, followed by 1 LZ0, followed by 1 LZ minus 1. Then the next row will be 0 LZ1, 0 LZ0, 0 LZ minus 1. Then the last row is going to be minus 1 LZ1, minus 1 LZ0 and minus 1 LZ minus 1. Okay, so now that we end up getting this, we are able to remember that LZ when operated on YLM is going to give you back MH cross YLM. So therefore the first matrix element will be MH cross with a with an integration of 1 and 1, which means that since these are orthonormal function, you're going to get h cross. On the other hand, 1 LZ0 is going to give you 0 times 0 back. So 1, 0 are orthonormal functions, so you're going to get 0, but anyway the prefactor is 0. And in this case, it's going to give you minus h cross 1 minus 1. So that also goes to 0. So now you realize what ends up happening is that you have a matrix element for this such that if you take H cross out, you have 1, 0, 0, 0, 0, 0, 0, 0, minus 1. So the trace of LZ for this is going to be equal to 0. We'll think and understand what this all means later, and even the determinant in this case is 0 because you have an entire row or column that has only 0 elements. Similarly, can you try to write what is the LX matrix? LX matrix will also be the same, but interestingly enough, you can't do LX directly, so therefore we are going to take the raising and the lowering operator, very similar to what we did in terms of the simple harmonic oscillator. So for the LX operator is going to be 1 L plus 1, 1 L plus 0, 1 L plus minus 1, 0 L plus 1, 0 L plus 0, 0 L plus minus 1, minus 1 L plus 1, minus 1 L plus 0, minus 1 L plus minus 1, plus there's a 1 over 2 that comes up, plus half times 1 L minus 1, 1 L minus 0, 1 L minus 1, and we know for a fact that each of the time L minus operates on 1, it's going to take to 0, 1, 0 is going to be orthonormal, and when you have 1 L plus 0, 0 is going to go to minus 1, so therefore 1 minus 1 goes to 0. Oh sorry, we are talking about L plus, so therefore this element will take 0 to plus 1, so this element will exist. On the other hand, this element will be 0. The same argument, this will be 0 because L plus on 1 is 0 itself, L plus on 0 is 1, so this will go, but on the other hand this element will exist. Here you have an L plus on 1 that will go to 0 plus 1, so basically minus 1, when you have L plus, this is also goes to 0, and in this case this also goes to 0. Okay, L minus will take this to 0 because you have 1, 0, and then 1, this takes to 1 minus 1, that also goes to 0. 1 minus, this will be 1, this also goes to 0 because you have a 1 minus L minus minus 1. Here this element will exist, this will go to 0, this will go to 0, this will go to 0, this element will exist, this will go to 0. So therefore Lx is going to be equal to 0. Now can we determine what is 1 L plus 0? This is going to be equal to 1 times square root of L into L plus 1, 1 into 1 plus 1 minus M, which is 0 times whatever, 0 minus 1, that will give you back 1, right? Actually has to be written 1 comma 1, 1 comma 1, 1 comma 1 and 1 comma 0. I'm writing it just with the M quantum number so that it's easy, so you get 1 back. Okay, so similarly the next element that we should look for is 0 L plus minus 1. 0 L plus minus 1 is going to be equal to 0 square root of 1 into 1 plus 1 minus of minus 1 minus 1 plus 1 with the 0 here. That is also going to be equal to 1. So therefore what do we have for L plus? L plus is going to be 0, 0, 0, 0, 0, 1, sorry, 0, 1, 0, 0, 0, 0, half times plus half times, same thing we are trying to look at here, it's going to be 0, 0, 0. L minus will also result in a 1 here, 0, 0, 0, 1, 0. So therefore what we can actually write Lx is going to be half times, you only have elements in the 1 2 1 2 2 3 because of L plus, and then 2 1 3 2, right? So you're going to have the diagonal elements, unlike um, and then 3 2. So this is how the Lx matrix looks. I'm sure you can build up the Ly matrix the same way. Of course, it's going to have an I by 2 that goes with it with several minus ones, and I'm guessing it is something like this. I'd request you guys to solve it and see what you end up getting. So if you're able to think about why am I putting a minus 1 here, because you have an I. If you want to keep Ly Hermitian, it's going to end up reversing the sign along these ones. So therefore I'm writing it this way. And if you're able to see, trace of the Lx matrix is also 0, trace of the Ly is also equal to 0. So this is an important property. The trace and the determinant will end up being same for all of these three. So an exercise that you might work out so that you understand what's going on is to determine what is Lx times Lz and see whether you end up getting IH cross Ly in this endeavor using a simple matrix manipulation. So we will be seeing all the other concepts which builds up upon whatever you have learned in the rigid rotor in the upcoming classes.